obliterate anything. Okay, we're recording, so that's fine. I hope you've all accepted that. I'm going to try and explain some of the work that's been going on since I moved to the southwest. Now, when I came here first, I was particularly interested in the chalk. I still am. And of course, this is one of the main sections on the south coast of Devon, which is really a fascinating succession. Some of it's not very accessible, as you can see, but nevertheless, it was what I thought I was going to be doing when I came to the southwest, and I have continued to work on that. But when you look at Plymouth Sound and you see the view out to sea from the famous Plymouth Hoe, this area was turned into a special area of conservation in April 2000. And when you look at this area, Plymouth Sound, you begin to think about the history of how it developed. And of course, we all know that probably Dartmoor was periglacial during glacial phases. But of course, since the 1960s, there's been arguments about whether there are moraines and other glacial features out in the middle of Dartmoor. And so that's obviously something interesting in terms of the development of our sea level history. And when we look at the latest map of the last Brit ice sheet, you can see that right down in the bottom, it extends to the Scilly Isles. It doesn't impact on the north coast of Devon and Cornwall, but we have most of the English Channel as being dry during the last glacial maximum. And here it is here, the Devensian glaciation, MIS2. And what we have in the southwest is a record of glacials and interglacials. And something that Chris Smart and I are looking at the moment is this very strange record here of marine isotope stage sediments within caves along the south coast of Devon. And they're adding a lot to the glacial interglacial story. So when you look at the southwest, we've got all the features you associate with sea level changes. We've got raised beaches, we've got submerged forests, we've got cave deposits which can be dated with mammoth tooth. And recently, just outside the city of Plymouth, caves have been found with reindeer, rhinos, all sorts of animals that are now being assessed and which probably date back to about 30,000 years. Within some of the terrestrial caves, we also have flint tools and we have hominin records, one of which is 42,000 years. So we can build up a beautiful chronology using the caves, using the marine sediments, and that's what makes it exciting. So what I'm going to try to do is just look at one or two topics, probably far too many on that list there, but they're all intertwined. So let's just think of why marine conservation and then move into the different subject areas. Marine conservation in the southwest began with no-take zones, which was basically to stop fishermen dragging their nets along the sea floor and removing sediment, removing sea fans, removing all sorts of delicate structures. Then along came special areas of conservation, and Plymouth Sound is one of those. That was a European designation. And the UK followed that up with marine conservation zones. And I was part of the group in the Southwest that were called Finding Sanctuary of all things. But we were setting up marine conservation zones within the area. We also have the Western Channel Observatory, which is managed by Plymouth Marine Laboratory. Not directly conservation, but it provides an awful lot of monitoring information that helps with conservation. Now, for those of you that don't know the Southwest, this is it. The basement is Devonian and Carboniferous. The Devonian in white and the Carboniferous in the ruled ornament. To the east of Exeter, we have the Permian, Triassic, and along the Dorset coast into the Cretaceous and Jurassic sediments that are so famous. Within the Southwest, we have all these estuaries, mainly on the south coast, but there are some in the north coast. And you can see the little stars where we've done some work. The area is characterized by granite bodies. You can see Dartmoor, Bodmin Moor, and there are 5 separate granite masses, although they're interconnected below ground. And associated with those, we have mining that has been going on since the 18th century. So that's the area we're going to be looking at. So we have a rear coastline, that's what it's technically known as geomorphologists, particularly on the south. These drowned river valleys are a product of post-glacial rise in sea level. We've got saltmarsh, mudflats, sand waves, seagrass meadows, and you'll hear me talk about maerl, which is a calcareous rhodophyte algae. The whole area of Cornwall and West Devon is a World Heritage Site for mining heritage. Now, this is great to help tourism, and it recognizes the mining heritage of the area. The only problem is that we're left with a lot of contaminated sediments, mine workings, and because they're a World Heritage Site, we're not allowed to clean these up. Apart from 1 or 2 cases where there was crystals of arsenic on some of the structures and they had to be removed simply for safety. So we also have farming, which doesn't help pollution. So let's just take one interesting little estuary, the Fal Estuary. It's one of the simplest, it's north-south, and you can see the shape of it. You can see it's a drowned valley system. And we've sampled this over a number of years, and you can see a couple of students here doing a project within the mudflats next to the saltmarsh. Further down the estuary, round about here, we have a more open estuary. And eventually down at the mouth of the estuary, we have got the connection to the open sea. So when we look at any samples from the Fal Estuary, you get the most beautiful benthic foraminifera. Absolutely no surprises. These are all what you'd expect to see in a temperate climate, intertidal estuarine, nearshore marine setting. So nothing of a surprise. Many of these species were described by Montagu, Millett, Heron-Allen, and of course the late John Murray when he was working for a year in the Marine Biological Association laboratory within Plymouth. When we look at the estuary, we can subdivide into a number of assemblages just based on presence, absence, and the concurrent assemblages. Again, no surprise, and we can relate these to the salinity down to less than 5 parts per thousand and up to normal marine at the mouth of the estuary near Polruan and the town of Foy itself. So again, behaves perfectly ordinarily, no surprises. Where things get a bit difficult are when you look at the catchment of the River Foy, and you can see the Bodmin Moor granite in pink, and all the mines associated with it. Now, most of those mines are at the margins of the granite or just inside what we call the country rocks, adjacent to the granite. Now, I've marked on that map 41. Now, there are scores more mineral workings, tiny little things run by one family or one person even. But these 40 are the main ones. And they've contributed, not in a pollution way, not in a damaging way in terms of pollution incidents, just simply background geochemistry entering the estuary. And we can look at the geochemistry along the estuary, and what we find generally is that we have within the standing crop of living foraminifera between 3 and 5% of the assemblage is deformed, sometimes quite badly, sometimes only minor changes in structure. And of course, it's tempting to say that this is down to the geochemistry, the pollution that's natural from the catchment coming into the estuarine system. And when we look at our assemblages in the Foy and look at the values that we have, you can see that if I pick on one of the other parts of the southwest that I'm going to talk about in a minute, the pollution incident of Restronguet Creek, you'll see that in some cases there are minor changes. I mean, nickel is virtually the same. Zinc is much, much higher in Restronguet Creek. Copper is very much more. Aluminium is more. So there are things different between the Foy, where we think we have a natural background level of heavy metal pollution, and we can test that by doing laser ablation ICP-MS on the tests of the foraminifera to see the concentrations of metallic elements. But if we go across to Restronguet Creek, here it is just on the Fal Estuary. Here's the city of Truro. Now, when this was declared a special area of conservation, Restronguet Creek was left out. Now, at the meeting where this was done, I really objected because I thought that the recovery from a pollution incident in Restronguet Creek would actually be useful science. And it was part of the story of the Falmouth and Helford special area of conservation. Anyway, it was left out. And you can see the red line goes across the entrance to it. You can also see the pattern of the Fal Estuary. Again, it's quite clear cut that this is just a drowned river valley. Now, we've rather oversampled this, including students from Exeter University. And we've shared some samples. You can see red dots all over the place. The ones in Restronguet Creek, which are the ones over here, and in the Fal, that's us mainly. Exeter weren't really interested in that. But nevertheless, it's all part of the story. Now, when you look at the Foraminifera, well, they're perfectly normal for the southwest of Britain. We do have some deformed individuals. We also have, and this is a bit of fun really, we found this charophyte. And in fact, this charophyte was completely unknown in southwest England. And Natural England wanted to know where it was living. And when Cornwall County Council applied to do some roadworks, they were told, no, you can't. We might have a rare charophyte here. Well, I kept my head down at this point because I knew the head of the planning department in Cornwall County Council, and he wasn't very pleased, particularly when he found out it was an oogonium of a charophyte that was stopping his roadworks. Nevertheless, it's all good, clean fun. Well, when we look at the samples, the one thing that we were over embellished with, if you like, is species of ammonia. And we had great variations in pore size, apertures, ornamentation. And just to give you a feel, I'm not going to go through all these, but if you want to study ammonia in every shape or form, this is a great place to come and do it. Now, the interesting thing is that down in the bottom corner here, you can see some very heavily deformed ammonia. You can also see highly ornamented ammonia, which very often aren't illustrated in major monographs. Now, the marine biologists in the MBA and the University of Plymouth believe that we can link the degree of ornamentation with the carbonate saturation of the water. And that's one thing we're looking at the moment. The marine biologists are convinced of this. I'm certain that might be a little bit simplistic, but it's really a good idea. And so far, the data do seem to confirm that that's the case. So yes, ammonia, great fun to study. Now, this is the pollution incident. Wheal Jane was a mine, and we had an exceptionally heavy rainfall one winter, 1992, and the mine completely filled up with water and flooded. And this is the entrance to Restronguet Creek with the Fal Estuary behind. I apologize at the quality of the photograph, but this is taken through the window of a Coast Guard helicopter, which explains the very bad quality, but it's the only photograph that I actually have. Now, if you look at this spit here, and then look at this map, you can see that spit there. And this is the map of zinc, although if it was copper or tin or any of the other metals, it would almost be the same. But using this map of zinc, what we have is the highly contaminated upper parts of Restronguet Creek. It gets less out through here. And if you go across to the River Fal, you can see that that area virtually remained pure and clean throughout the whole of the incident. So what we've got in this exercise, and this I should point out, is a map of the sediment contamination 9 years after the event. and everything was still very rich in metals. We looked at the Fal Estuary, and all the way through the samples that we had, we could see deformed specimens. Again, we checked with laser ablation that it was actually real and it wasn't just surface contamination. It was actually within the carbonate of the shell. And the three at the bottom you've already seen, they're from Restronguet Creek. So when we look at the percentage of deformed individuals, you can see that this is the north bank of Restronguet Creek. This is the south bank. And after the pollution incident, which was at the beginning of 1992, you can see that although it's fluctuating, quite a lot of the time on both banks, we have levels well above the 3 to 5% that we saw in the Fal Estuary. We then, for various reasons, well, to be honest, I took over as Pro-Vice Chancellor in 1996, and between then and 2004, I wasn't looking after students that we could take out and get any more data. So sorry about the gap. But the interesting thing is that when the sampling started again, we were still recording levels that were much, much higher than background that we see in other estuaries. And it still continues today. Although I haven't plotted a graph to show the data, we are still trundling along at well above the 3 or 5% average for a normal estuary in the southwest. So how did Restronguet Creek recolonize? Well, there's migration of species. That's not really possible because to have migration of saltmarsh species through more marine environments, that's just not going to work. The bird's foot model, well, that produces a random introduction of species, and I'm not sure I believe it. Obviously, propagules being washed in on every tide would give you the mechanism to get the saltmarsh and upper mudflat species into an environment that otherwise couldn't be the case. I think we need to do some more work on that, and it's still on the agenda to do. Although sometimes at my age, I feel I'm running out of time to do this, but nevertheless, it's still interesting. So let's think of our estuary we started with. Plymouth Sound, we did drill some boreholes in Plymouth Sound. I keep asking for some more, but it's quite expensive. But in this particular case, you can see that the old channel of the River Tamar is heading out to sea. Now, of course, the breakwater wasn't there then. This just went straight out to sea. But looking at the borehole here, what you have is down at the bottom of the core that we took, salt marsh and upper mudflat. Then we've got estuarine with typical foraminifera, and then shell-rich sands with increasing marineness up to the top. Just at the top, the area here converts back to mud. And the reason for that is they built the barrier across the entrance to the sound, and that created a change in the sedimentation pattern. So this is an interesting exercise, and it would be lovely to drill some more cores. And now that we're a national marine park, I'm promoting the idea that they give us a few more cores to deal with. Of course, we're very fortunate. We have our own boat in the university. But we also have access to the Plymouth Marine Lab boat and the MBA boat, Sepia, here. Here we are on Sepia with Murray Grab. John Murray's father, George Murray, designed a sampling device that closes off the sample to stop fine sediment washing off as you lift it back out through the water. And this is us using it off the back of Sepia. If I recall rightly, this is a young Tracy Hayes as a project student, looking rather cold. It was the 6th of February, and don't remind me that it was my birthday, so they took me out on my birthday sampling. And poor Tracy made a lovely cake with a candle, but was told it was a fire hazard on the boat, told to put it out. So it was all good fun. But this is another cruise on Plymouth Quest, where we go out collecting box cores. These people are all doing biological identifications. We just collect the box core and bring it back to the lab. When you look at Plymouth Sound, there are sand areas in yellow, mud areas in orangey color. And when we look at diversity or production, however you measure it, the sandy areas come out at this end of the diagram, the muddy areas, quite obviously because there's more food there, come out here. Now, all our figures of living foraminifera are smaller than those calculated and collected by John Murray in his work in the 1950s and 60s. Plymouth has undergone what's called a clean sweep, and that's basically removed most of the nutrients from Plymouth Sound, and the living population of foraminifera has gone down. We can see coastal features like this. Here's a French example, which is rather bizarre. But in these boreholes, or some of these boreholes across between Jersey and France, you can see down at the bottom, we've got a saltmarsh assemblage. Then we've got an estuarine mud assemblage in yellow, and then a marine assemblage. And we've just recently run through the stable isotopes for all this. And also, because there's a peat right at the bottom, we've been able to date that peat. It's interesting that just below that peat, there are some Eocene sediments which contain larger foraminifera, but that's another story. The peat plots here, very close to the Massey et al. Sea level curve, for the southwest of England. And using this particular core, you can see the peat in black here. We have a very nice record of increasing marineness, and there are a couple of levels in here where you find mearl. And I'll come back to them in a minute because they're slightly unusual. But one of the other features that I can't mention the Southwest without raising it is the seagrass meadows. All the climate change individuals are getting excited about the fact that they sequester carbon dioxide in the seagrass. Well, unfortunately, even about 10 centimeters below the surface, there's no seagrass left. So they might sequester it at the time, but it doesn't stay sequestered. The other thing is that the calculations by the marine biologists forget the fact that there is a distinctive assemblage of calcareous benthic forams associated with seagrass, and they leave that out of the calculations. But then, of course, it takes a micropaleontologist to put them in. We've modeled this. I should have a seahorse in here, but I can't draw a seahorse. But we do have seahorses. And when you look at these epiphytal foraminifera, Most people think of Cibicides with a flat surface, but actually most of the epiphytal foraminifera in June or July are elphidium. And this was one frond of a seagrass plant taken back to the laboratory, stained with rose bengal, and it is just awash with elphidium crispum. And that seems to be normal. We did some experiments with elphidium, and basically elphidium always crawls out of the tank, even if it probably endangers itself by doing so. So they always crawl up things, whether they're crawling up the fronds of the seagrass to get some advantage, I really don't know. But of course, you can imagine the fun when in a chalk quarry in the Netherlands, what we found was seagrass. This is seagrass. And my Dutch colleagues couldn't resist drawing a mosasaur eating various Cretaceous ammonites and belemnites surrounded by seagrass. When these fossils were first described back in 1853, this was upside down, and these were supposed to be the shoots. Well, actually they weren't. They're the rootlets, and these cross sections show just how beautiful the preservation of the seagrass can be. Now, these are the rhizomes. They are in the chalk here, silicified. And the preservation is just quite stunning. Of course, the interesting thing is, and this is a digression, grass is thought of as a Cenozoic feature, but did grass develop in the sea during the high carbon dioxide levels of the Cretaceous? Well, these are certainly Cretaceous. We can see epiphytal foraminifera. We can see larger foraminifera in the root system. So it's really quite useful to see this seagrass community and base it on what we know. So what are the threats for the future? Well, climate change, more extreme events causing major runoff, which creates turbidity of the water, and that happens quite frequently. Ocean acidification will change the balance of carbonate secreting organisms, particularly mearl. Temperature rise, dissolved oxygen diminishing, and sea level rise, causing erosion of salt marsh environments and migration of shorelines. Acidification we tend to know about, and the marine biologists in Plymouth are really quite concerned about this, although we've looked at this in terms of planktic foraminifera and pteropods around the Caribbean Sea, where the pH of the water was very much affected by volcanic eruptions. Again, that's another story. Look up an issue of micropaleontology a couple of years back. Mearl is really fantastic. I collected some rhodoliths from coastal Brazil, which I probably wasn't supposed to. I've even found fossil rhodoliths in Hungary, which were Albian in age. But the mearl itself is really quite delicate, and they're always written about as high biodiversity environments. Now, when we processed samples of mearl from the Fal Estuary, all the foraminifera were transported, including from saltmarsh. So these weren't living, I don't believe, in the mearl. It was simply trapping it as it was being moved around on the sea floor. So mearl's an interesting story, and there's a lot more work to do on that. And the relationship between mearl-rich environments and foraminifera. This is Jason Paul Spencer's slightly gloomy model of what will happen to mearl in acidification. Most of the mearl that's dead down here disappears, as do many of the bivalves. And what we're left with is a much more abundant assemblage of seagrasses and algae, but the mearl beginning to suffer with acidification. Now, we were looking at this out in the island of Ischia, although the sections we looked at have now been wiped out by a flood and a landslide that came down and completely demolished the area we were working in years ago. And here we had carbon dioxide bubbling through seagrass. And when you looked at that environment, you saw here we have a normal pH sample, a reduced pH sample, and then a completely reduced pH sample. And you can see the change in the assemblage, you can see the change in the percentage of calcareous forms, and you can see the change in diversity. But of course, when we're looking at saltmarsh and estuarine conditions, we have to be very careful that calcareous forms can dissolve just below the surface in salt marsh and mudflats. And that's due to the pH of rotting vegetation and things like that. So when you're left with an agglutinated assemblage, you really have to make sure that it is a diagnostic agglutinated assemblage and not something that's been left by modern biodegradable salt marsh vegetation. This particular case in the River Otter, they've removed the coastal barriers, the coastal protection, and the area is now converting to salt marsh and mudflats. We were hoping to monitor this marine incursion, but then a little incident called the global pandemic arrived, and we're slightly behind in getting that monitored. But it's an interesting project to look at coastal realignment and use foraminifera to study the environments that we are now creating as part of coastal management. Well, I think I've said enough. The estuaries of the Southwest are a fascinating story. When we look at boreholes into these estuaries, we can see a record of glacial or post-glacial sea level rise. We can fit that into the story of the terrestrial caves and now the marine caves. I mean, this must be one of the few areas, possibly in the world, where you have marine caves with a foraminifera record. Now, they're all being washed in. They're not living in there, of course. They're all being washed in. And when you look at the grain size, you can see that they're a particular grain size, which indicates they've been picked up and transported. But these marine caves were above sea level during the glacials when sea level was lower. And they've only been inundated during interglacials. And so we have this very peculiar record. It's slightly bizarre. I did give a talk on this recently, and people were asking whether or not I'd done my own cave diving. Well, at my age, I'm not about to take up cave diving, but fortunately, we have a total enthusiast for doing that, and he provides us with the samples. So watch this space. It may get to the Forams meeting in Perugia if we get some of the work done on time. And just to finish off with, I'll advertise the Perugia meeting and the session that we are hoping to introduce to really recognise, if that needs to be said, the fantastic career and work of the late John Murray. I was delighted to have known John for a great length of time. Although we actually did only a few editorial projects together, we never seemed to manage to look at samples together. But nevertheless, my library contains several box files of his contribution to science, and we hope to celebrate that as part of the Perugia meeting. Anyway, I will end at that point and let you loose on any questions that have come into the chat or anywhere else. Thank you all for listening.
Thanks very much, Malcolm. There's some virtual clapping going on. Right, so that was a great talk. I loved all the images as well, and the lovely South England countryside. It looks nice and warm there, and just, you know, almost tropical sometimes. And I'm sure it's a brilliant environment to work with, although sometimes quite challenging as well, right? So I was just going to open up to anybody, if they have any questions, if you could please raise your hand, and then we can unmute you to ask the question. Or I can read out the question as well, and it doesn't matter. So we have Mike Bidgood. Jaume, would you be able to unmute Mike Bidgood so he can ask his question?
Oh, yes, sorry.
That's okay. There we go.
Hello.
Hi, Mike.
Hi. Great talk, Malcolm. Thank you. I was just wondering about the deformities recorded. Do the deformities occur throughout growth, or it looked to me as if some of them were quite late stage?
Yeah. Hi, Mike. Nice to hear you. For those that don't know, Mike is a former PhD student of mine, so he's getting back at me for asking questions. I actually don't know the answer, Mike. I suppose what I ought to do is micro dissect some of these specimens. You're correct in the sense that they seem to show up in the adults, but really that shouldn't be necessarily the case. One should expect to see it almost impacting on the earlier growth stages. Somebody asked me this question before, and I wondered what would happen if you had a deformed specimen as a juvenile. Would it actually survive through to adulthood and whatever? I don't know. Those people who do micro dissections of foraminifera maybe should have a go at this and see if they can work it out. But I don't have an answer.
It was just, I was looking at the SEM images, and it occurred to me that some of them looked as if the deformities, I think it was, is it Ammonia aberdaviensis?
Yeah, that's right.
Kind of looked fairly deformed all the way through, and yet there was the Hainesina germanica where it looked as if it was only the final couple of chambers that looked a bit odd.
Yeah, in some of the Elphidiums and Hainesinas, it can just be slight deformity in just one of the chambers or an additional chamber. And that certainly looks relatively late stage. The really deformed ones that we found in Restronguet Creek, as I say, we ought to try and micro
Yes, yeah.
dissect these and have a go.
You need a steady hand.
Yeah, that's true.
Okay,
Right.
thanks, Malcolm.
Thanks, Mike, for your question. We've also got a question from Katia Barbosa. Katia, would you be happy to ask your question?
Oh, hi. My internet's not very good today. Can you hear me?
Yes, yes, fine.
Congratulations for the talk, Malcolm. It was really wonderful. And I would like to ask you about the Propagul's hypothesis. Why not just thinking about tide come and going?
Yeah, that was what we thought of originally. Whether or not a juvenile living foraminifera could survive the marine conditions that it has to go through to get into the higher mudflat, I don't know. I know that there was an interesting paper by Anna Wienman and Sue Goldstein on a mudflat area on the east coast of the United States. And they came down on the side of propagules moving landward. I think I'm probably being swayed by that interpretation rather than thinking of another one. It did seem to fit the model, but I mean, we always look at what else is being transported in, just in case there are clues from other taxonomic groups. And we don't see wholesale transport into the ends of the estuaries because we are talking about quite long distance, well, relatively long distances up into some of those dead end estuaries. And the amount of flow of water, well, yes, there is a flow of water, but it's very calm, very gentle, and it's not function of storm conditions. So I think you've got to find a mechanism that is going to operate in quite quiet conditions. It's just an idea, which we'd love to test a bit more.
Yeah, quite good. Thank you.
Great, thanks. Then there was a question about whether ocean acidification is linked to global warming or pollution and things like that. Malcolm, if you want to comment on that.
Yeah, I saw the question come up on the screen. I mean, ocean acidification is a function of the transfer of carbon dioxide into the surface waters of the oceans. And the biologists tell us constantly that about 30% of the carbon dioxide produced during the global warming process, about 30% of it goes into the oceans. And it changes the surface water acidification. There's quite a complex model by Caldera and Vickett, well, nearly 20 years ago now, 18 years ago, which showed that the impact in the oceans was surface and didn't go down very deep, or at least not very quickly. And I think it's part of the process, but it only affects surface waters, which of course is why small juvenile planktic foraminifera, pteropods, heteropods that are up in the plankton show more signs of acidification damage than the benthic foraminifera. And when we were working on the end Cretaceous, I know this isn't modern, when we were working on the end Cretaceous, we had a view that the surface waters after the bolide impact and the CO2 increase, they were affected by acidification. But the benthic foraminifera that were in 50, 60 meters of water showed absolutely no sign of dissolution at all. And so you can see that it's a progressive change down through the water column. And the models of Caldera and Vickert, they really say that we're going to be well into the next century before it actually gets too far down in the water column, even at the increased rate of CO2 production that we're going through. So it's a shallow water feature in most environments, and we've reported that in around the island of Montserrat, where the volcanic ash was changing the acidification. And as I say, we found the same story when we were looking at the Cretaceous tertiary boundary. So it seems to hold water, although there's a lot more work needs to be done on it. And I just wish we could get more work on nearshore plankton and benthos to see what that profile is between the surface and deeper water. Massive job, and you need a very well-trained bunch of marine biologists to help you work on that. Fortunately, we've got a few in Plymouth with the marine biological labs, and they really are very, very helpful.
Sorry, my kids are discussing stuff outside my door. Malcolm, thank you very much. And so one last question. So we have quite a few early career researchers here at the talk today as well. Do you have any career advice for them, some tips on what to do or what kind of, new emerging areas you might see developing?
Well, I just keep thinking of things that ought to be done. It's rather not depressing, but when you realize you're running out of road for doing some of them, it's a little bit embarrassing. I think the very big importance to the work that we need to understand in terms of the climate change, the acidification, the changing oxygen levels in the seawater, we really have to link with our marine biology colleagues and look at whole environments. Just looking at the foraminifera, yes, that's interesting, but I would say and stress working with marine biologists, oceanographers. I just saw a message from Julia come in from Portugal. Some of the institutes that some of our younger scientists are now working in do have that opportunity for cross-discipline work. And I think that's important. I mean, I ended up where I did by almost total accident, because when I was a student, I was sent out to the French Alps to map an area which was all above, it's all above 3,000 meters. I was fitter then. But all the rocks I looked at were full of microfossils. So I got into microfossils as an undergraduate. And apparently I did so well at that my supervisor told me to join the team down at the Channel Tunnel and start working on the Channel Tunnel. So, I mean, I didn't have a decision to take. I just went along with what was happening. But to take a positive decision, get to know your marine biologists, work with them, look at the whole environment, not just the foraminifera. That would be my advice.
Great, thank you very much. If you just stay on, but we'll close the seminar and we will stop recording as well now. But thank you all so much for coming and joining us. And remember, on the 30th of March, we've got Adriana Lam giving a talk about new gene plankton foraminifera evolution. So look forward to seeing you there.